So it's my great pleasure to welcome you, and thank you very much.
Great. Hi, good morning, everyone. So first of all, thank you, Lauren, for the introduction again. And thank you very much for the invitation. And also thank you for giving the opportunity to give 2 talks. It's my great pleasure to be here. So in this presentation, I want to show you some recent research progress in my research group about modeling and simulation for metal additive manufacturing. So this work was mainly done by my PhD students, Qiming Zhu, Ze Zhao. There are a little bit of experiment which was done through my collaborator, Mohammed, at the Applied Research Institute at the UIUC. Qiming actually was a graduate student here before. He was working with Dominic, and he has co-authored a paper with Lauren, Cassie, in Journal of Wind Engineering and Industrial Aerodynamics. So it's really great, to show some of his work here. So the title of my presentation is a mixed diffusive-Sharp interface approach for multiphysics modeling of metal additive manufacturing. So this is the outline of my presentation. I will give you some background about what is metal additive manufacturing and show you the challenging of modeling and simulation of a metal additive manufacturing process. So metal additive manufacturing is a very unique type of interface-coupled multiphysics system. So from the perspective of computational mechanics, the challenges can be summarized as 2 points. The first one is how do you effectively handle the material interface evolution that undergoes topology changes? Number 2 is how to actually enforce the critical boundary condition, especially the Neumann type of boundary condition on those material interface. So I will show you 2 existing approaches you can utilize to solve this problem. One is interface capturing, another one is interface tracking. I will briefly summarize the pros and cons of those 2 approaches and tell you the motivation why we want to develop a mixed interface capturing and the interface tracking formulation. I will show you all the details of this mixed formulation. I will talk about thermal multiphase flow. One byproduct of this mixed formulation is a geometry-based redistancing technique for level set method. I will show you this as well and compare its performance against the traditional PDE-based redistancing for level set method. I also want to show you some preliminary result of a recent developed coupled level set and enriched immersed boundary method, which we feel have a great potential for general interface coupled multiphysics problems. So during the presentation, I will show you how you can utilize the models we developed to predict the critical quantity of interest during metal additive manufacturing process, with focus on defects, surface roughness, and the powder spattering. So what is additive manufacturing? As some of you may know, metal additive manufacturing, such as laser powder bed fusion or directed energy deposition, is a type of manufacturing method that utilizes the high energy density laser to melt and center metallic powders in a layer by layer fashion to produce 3-dimensional structures. So compare with the conventional subtractive manufacturing method, metal additive manufacturing offers several advantages. So first of all, it can fabricate really complex geometries which are hard for conventional subtractive manufacturing method. It offers tremendous design flexibility, and it also helps reduce material waste during the manufacturing process because of its additive nature. However, one issue in metal additive manufacturing is that the 3D printed parts are prone to defect, porosity, and the rough surfaces. So currently, right, how to predict the process parameters affect the development of those defect, porosity, and roughness are very challenging. And how to derive the process structure and property relationship is still an open question in the metal AM community. The reason is because metal additive manufacturing, as I mentioned, is a very challenging interface-coupled multiphysics problem. So here I want to use this video to illustrate some of the challenges. So what you see here is a selective laser beam melting process revealed by Argonne National Lab using high-speed, high-resolution X-ray imaging, you see that during the printing process, the laser material interaction leads to very complicated interface evolution. The interface, what I mean here, is the gas-metal interface. You see the so-called keyhole instability. You also see a lot of gas bubbles are generated due to the keyhole instability. And if those bubbles, like this, couldn't escape from the resonified materials, they become defects, which can degrade the quantity of the printed part. So accurately, robustly, handle the gas-metal interface evolution and enforce the boundary conditions on the gas-metal interface is very, very important, right, for the modeling. However, this is, as I said, this is very important. The reason is that the gas-metal interface is the central location where the metal AM physics mainly take place. So across the gas-metal interface, you have the interplay between fluid mass and the heat transport. You have phase transitions such as melting, solidification, and even evaporation. And you have a very large property ratios across the material interface. And as you already seen, right, from this video, the interface can go violent topology interface changes. And more importantly, on the gas-metal interface, you have a set of critical boundary conditions, especially the Neumann type of boundary conditions that needs to be satisfied simultaneously. So the boundary conditions include heat flux, laser heat flux, surface tension, Marangoni stress, and the recoil pressure. So in computational mechanics, there are two existing approaches you can utilize to tackle this problem, depending on how you handle the interface. The first one is so-called interface tracking. I believe the most famous approach probably is the arbitrary Lagrangian O'Neilling approach, ALE. So in this type of approach, the material interface is represented by a deformable mesh, right, as you see here. In this interface tracking approach, the interfacial boundary conditions are applied directly as traction or flux type of boundary condition if we are using finite elements. The advantage is that this type of method has high accuracy per degree of freedom. However, in order to track the interface, you have to perform mesh motion and sometimes even remeshing. And you can see that given the topology changes of the interface you see from the previous video, it's almost impossible to apply this approach to realistic printing process. The second approach you can utilize is the interface capturing. It has so many variants like level set, volume of fluid, and phase field. So in this type of approach, the interface is implicitly represented by a scalar field. And in order to capture the interface evolution, you need to solve additional scalar partial differential equation. So in this type of approach, the interfacial forces or fluxes are normally applied as a body force and turn in the conservation laws. I will give you more details later in my presentation. The advantage of this type of approach is that they are very flexible. They do not need any mesh motion and remeshing because everything is embedded into the partial differential equation, the topology changes. So it can handle the topology changes automatically. However, since you don't have an explicit representation of the gas-metal interface, it is not very straightforward to handle the laser material interaction in additive manufacturing, such as the multiple laser refraction in the keyhole. Okay, so given the advantage and the disadvantage of those two existing approaches I just presented to you, we feel that mixing the two approaches probably is the best way to go. So our goal is this. We want to explicitly track the moving gas-metal interface without losing mesh flexibility. What I mean by not losing mesh flexibility is that I don't want to do any mesh motion. I don't do any mesh regeneration. I just have an initial mesh, and I use the mesh throughout of my simulation. So how to do that? The idea actually is very simple. Probably you see something in the literature as well. So the idea is follows. We first utilize the interface capturing approach, which in this case is a level set to capture the interface evolution. So if you have studied level set a little bit, you know the level set basically is a signed distance function with respect to the gas-metal interface. And the gas-metal interface is implicitly represented by an implicit function phi equals 0. We only use the level set to capture the topology changes. That's all. And after that, we go to interface tracker. So basically what we do here is we extract that explicit representation from the zero level set after you solve the level set convection equation. You may feel this is very complicated given the, the topology changes of the interface. However, if you stick to unstructured tetrahedral mesh, it's very simple because if there is a intersection between the zero level set and the tetrahedral element, there are only two intersection scenarios. In scenario 1A, you have 3 intersection points between the narrow level set and the element. You can simply connect those 3 intersection points. You form one triangle. In scenario B, you may have 4 intersection points. Do the similar thing, right? Form 2 triangles. After you get all the triangles, you build the connectivity, you will have a triangulation of the gas-metal interface. This triangulation holds for any scenario, even though your interface is, no matter whether the interface is simple connected or multiple connected, it doesn't matter. And you see the triangulation is done in an element by element wide fashion. So it's extremely easy for parallelization. It's really fast. And after you get all the triangulation of the gas-metal interface, as I will show you later, this can significantly facilitate how you treat the laser metal interaction. One byproduct of this mixed formulation is a geometric-based redistance. So as I said, right, level set function is the signed distance from a point to the material interface. However, due to the strong convection, this signed distance property may be lost during the simulation. So people normally need to recover this property by doing redistancing. So conventionally, what people do is to throw the so-called Eckler equation, right? This is a pseudo-time independent Eckler equation here. And the advantage of this approach is that it is very flexible. You basically can use any spatial discretization to solve this PDE, right? But however, you still need a PDE solver. And this method, right, still needs to use several numerical parameters, not physical parameters. You need to properly choose those parameters, such as the interface thickness and the pseudo-time step in order to achieve the best performance. Now, remember, in our mixed formulation, the gas-metal interface is represented by triangulation. So the signed distance can be explicitly computed by using geometric relationship. So what you can do is for a given point in your mesh, you can just directly compute the minimal distance between the point and the triangles, right? And then this will be your signed distance. I mean, of course, you can use some brute force algorithm. In that case, your complexity will be On, where N is the number of triangles in your triangulation, right? But you can always, organize the triangulation in a work tree structure, so you can reduce the complexity from On to O log N. So it's very efficient, and you will get signed distance properly recovered everywhere in your computational domain. So before I show you how we apply this mixed formulation to additive manufacturing, I want to quickly show you some comparison between the conventional PDE-based redistancing and the geometric-based redistancing in the context of benchmark multiphysics problems. The first problem you see here is a pure convection problem, which is the Lasky rotating sphere. So here you have a slotted sphere. So the sphere will be convected by a given and a periodical velocity field. If your numerical method does a perfect job, the sphere should be preserved its shape and just does rigid body motion. So we simulate this problem by using geometric redistancing and PDE-based redistancing for 2 cycles. So here is the comparison. Barely, I would say the performance are almost equivalent. However, if you take a closer look at those boxes I'm highlighting here, you will see a little bit edge of the geometric redistancing. Now let me show you another problem. The second benchmark I want to show is the static bubble in an inviscid liquid without gravity. So this is also a very famous benchmark in the multi-phase flow community. Since you don't have a viscosity, you don't have a body force, so the Navier-Stokes equation will be reduced to the so-called Young-Laplace equation, meaning that the pressure difference across the liquid-gas interface equals to surface tension times 2 divided by the radius of the bubble. And then you shouldn't have any velocity in the computational domain. So here we did a refinement study for this problem by using both PDE-based rate descent and the geometrical-based rate descent. This is a pressure field. You can see that both of them are converging, right? And you couldn't see any difference. I would say the performance for those two approaches are equivalent. Both of them are converging and they deliver very good result. However, if you check the velocity field in the computational domain, you will start to see geometrical-based rate descent deliver a much better result. As I mentioned, right, theoretically, you shouldn't expect any velocity in your computational domain. However, when you solve the problem in a numerical setting, you always expect some velocity. This velocity is called parasite currents in the multi-phase flow community. But however, smaller current magnitude means better method. And you can see that for the three meshes I'm using here, geometrical rate descent always give you much smaller velocity compared with the PDE-based counterpart. So with those comparison, let me show you how we utilize this mixed formulation to facilitate the laser-metal interaction. So what we do is as follows. Okay, so for a given laser profile, we first divide the laser into multiple rays. And for each ray, we will track all the intersection between the ray and the gas-metal interface. Now you need to remember your gas-metal interface is represented by a bunch of triangles. So this can be explicitly done. So traditionally, if you use interface capturing, because this interface is implicit, right? You have to solve additional equation in order to handle this laser reflection. Normally people do solve a radiation equation. But now this can be done, as I said, right, in a pure geometrical way, right? Even, as long as you have a little bit geometric understanding, right, you'll be able to know how to do that. So for each intersection point, how much energy will be absorbed, how much energy will be reflected are given by those three equations, which depends on the inclined angle as well as the thermal properties of the alloy you use for printing. And we track all the intersection point between the ray and the gas-metal interface until either the ray leaves the domain, leaves the melting pool, or the ray energy becomes sufficiently small, and then we stop. And then we do this interaction between every ray and the gas-metal interface. And for each intersection point, the absorbed energy will be distributed around the intersection point as a Gaussian profile. And after you get all the Gaussian profile, you add them together. This becomes your final laser hidden loss. And then how we incorporate this hidden loss, we apply the Bragg-Beal continuous surface force model, meaning this heat flux will enter the energy conservation as a body force enter. So with this, let me quickly show you, what is the multiphysics model we use for metal additive manufacturing, right? So our approach is based on a thermal multiphase flow. So here I summarize the partial differential equations we are solving in the model. So first of all, the material flow is governed by the the conservation of momentum and the conservation of mass. This is also the so-called Navier-Stokes equation, right? However, because evaporation may happen during the printing process. So purely in the gas phase or purely in the liquid phase, the flow is incompressible. However, across the gas-metal interface, because of the evaporation, the flow can be slightly compressible. So we have a model to account for this. And then the temperature field is governed by the energy conservation. Here, the energy conservation is written in terms of temperature unknown. And then the last equation is the level-set convection, because I still have an interface capturing approach here, right? And then the boundary condition, this is very critical. So we consider all sorts of boundary conditions on the gas-metal interface. So for mechanical interfacial forces, we consider surface tension, Morangonian stress, which is also the time-dependent surface tension, right? And then we also consider the evaporation force as well as the recoil pressure. And then from the thermal side, we consider, in addition to the flux from the laser I just showed you, we also consider the heat loss due to evaporation and the radiation. And we solve, and all of those boundary conditions are handled by the Bragg-Beal continuous surface force model, which means all of those boundary conditions will be converted into body force and turn in the momentum equation, which actually have some issues. I will show you later on in my presentation. But right now, this is what it is. And then how we solve the PDE, and we are using a stabilized finite element method to solve all of those PDEs in a fully coupled way in order to achieve the best, in order to achieve the best robustness. Now let me show you several applications. I will first start with several validation cases, and then show you some real-world applications. The first validation you see here is a stationary laser melting process. This process has been experimentally investigated by Argonne National Lab using high-speed and high-resolution imaging. This figure shows you the simulation setup, so you can see what are the materials we use for the metal phase and the gas phase. And you can also find the laser parameters here, as well as the size of the computational domain. And here is the simulation result. So the background color indicates the temperature field, and those gray arrows shows you the heat-induced evaporation jet. And you can see that our simulation captures the so-called transition between conduction mode to the keyhole mode very well. You see that in the beginning, before your maximum temperature reaches to the boiling point, you have a very well-behaved keyhole, right? Very stable. And once the maximum temperature reaches beyond the boiling point, the keyhole start to become very unstable, right? You see a lot of fluctuation. And this fluctuation is reflected in the time history of the melting pool depths. You see that once you reach to the boiling point, right, the keyhole steps start to have a very strong fluctuation here. And then after you do the simulation, you can compute the recoil pressure. If you integrate the recoil pressure over the surface of the melting pool, you get the so-called surface recoil force, which you also see very strong fluctuation. This fluctuation explains why you have the fluctuation for the melting pool depths, right? Because this surface force pretty much is a pressing force on the free surface, right? If your force have a lot of fluctuation, of course you can result in fluctuations in the melting pool depths. This is just a validation to show you that our computational model, right, is able to capture the keyhole morphology very well. So this is the experimental imaging, and this is our computational result. Okay, another validation case, which is also a stationary melting process. This case is very fresh, which is coming from the NIST 2022 NIST EIBM modeling challenge. So what you see here is a selective laser beam melting process, stationary laser, but over an inclined surface. So this is a blind comparison, which means the NIST only released the manufacturing parameters. You run the simulation, you submit the result, and they do the comparison. So the video here you see is the X-ray imaging from NIST, and the video in the middle is our simulation results. So similar stuff, right? Temperature, keyhole instability. One thing I want to draw your attention is that you can see how well the model captures defects, developers, right? And how these defects or gas bubbles get trapped in the resonified material after you turn off the laser, right? And this plot shows you the time history of the energy absorption during the printing process. Again, you see very good correlation between simulation and the experiment. And this model actually got a prize in the 2022 NIST EIBM modeling competition. Now, of course, you can let your laser move. So what you see here is a moving selective laser beam melting process. This is also a process, right, investigated by Argonne National Lab. And you see similar stuff. Here we place the camera on the laser and move together with the laser. You see similar stuff, right? Keyhole instability, those free, fog stuff is the evaporation-induced jet. And you also see, right, a lot, a very big, significant, right, substantial, right, free surface deformation. And this free surface deformation will result rough surfaces during the printing, in the printing. So this you are looking from the top. This is the top surface of the substrate, right? And then this is the evolution of the surface. And here is the experiment. And you see that, the model can capture the surface roughness evolution pretty well. You capture the so-called shelving feature, which is a series of V-shape, right, along the printing direction. And this is another validation for the keyhole morphology. You see very good correlation can be found between the X-ray imaging and our simulation. Okay, and this plot shows you the time history of the melting pot dimensions. Argon only measured the mean of the melting pot depths. So for here, I want to show one phenomenon which is very interesting. So you see that right for the melting pot depths, when your laser is moving, you see fluctuations, but the fluctuation is very small, right? It's much smaller compared with the depth fluctuation for the stationary laser case. We didn't do parametric study, but this modeling result actually support one finding from the experimental investigation from Argonne National Lab. So Argonne found that increasing scanning speed actually can suppress the melting pot depth fluctuation with and without the powder. For both, you see that, right? As the scanning speed increases, you see the relative fluctuations decreases as well, right? This is also found in our simulation. And if you compute the surface recoil force, similar thing, right? You have a fluctuation, but the fluctuation is much smaller compared with the fluctuation of the surface force in the stationary case. This explains why you have a smaller fluctuation in the melting pot depths, right? Okay, so those are just the validations, right? We don't consider powder, right? During the printing process, Argonne didn't consider the powder bed either because they want to generate some experimental data with minimal uncertainty, right? Because if you have a powder bed there, it's very hard to know what is the initial powder bed distribution. However, we did some work, right? Involves powders. So one critical issue in additive manufacturing is the powder spattering. So in our simulation, previous simulation, I showed you, you see the evaporation jet, right? Due to the laser material interaction. The jet sometimes can be extremely strong and even blow away metallic powders. This is called powder spattering. If the redeposited spatters, if the powder spatters are redeposited on the powder bed, they can cause lack of fusion and rough surfaces. So in order to clear the spatters, what people do is to apply the ambient cross flow to clear the spatter. However, there is no modeling tools right now in the industry that can tell you for one specific machine how to optimally choose the cross-flow parameters to achieve the best mitigation strategy, best mitigation performance. The reason is because this is a multi-scale problem. So let me explain why. So you see this spatter, right, happens first at the powder scale. This is at the micro scale meters. So the average size of these powders are normally around 50 to 100 micrometers, right? And after the spatters are injected into the machine chamber and the migration of those spatters due to cross flow actually happens at a meter scale, maybe this big, right? So there is a huge difference between scales. So how do you study them, in a systematic way, right? This is a big challenge. So recently we developed a very engineering approach. So I just show you a mixed formulation of a multi-phase flow for powder scale simulation, right, at the powder scale. So what we do here is we couple this mixed formulation of a multi-phase flow and the DEM simulation to first simulate the powder spatter injection. After we do the simulation, we extract the injection angle, injection speed, as well as the vapor plume jet. We do a parameterization. And after that, we feed those information to a bigger chamber scale CFD model coupled with DEM model to simulate the particle migration inside of the machine chamber. So this chamber scale couples aerodynamic CFD and the DEM, and it takes the information from the powder scale and the cross flow to do the spatter dynamics. In the morning, I just had a discussion with Jialiang. He told me that the very early work of DEM actually was done here. I didn't know that. Otherwise, I would show some details about this DEM work. But I would say our DEM is way simpler, right, than the DEM model Jialiang mentioned to me in the morning, because you see in additive manufacturing, the mechanical powders are spheres, right? So it's really easy to handle the collision. Anyway, right, we have a multi-scale model, and least we coupled, right, the powder scale and micro scale, and the chamber scale and meter scale, right? Although it's a one-way coupling, but at least you show some coupling there, right? We actually did some experiments at UIUC by using 3D printer donated by GE Additive, and then I will show you some results. Okay, so let me first show you the chamber scale model. So this is the machine chamber, right, of the machine you saw in the previous slide. And we build a detailed model of this machine chamber. So this is the CAD model. You see we resolve all the geometric details inside of a chamber, including platform, reservoir, gas flow inlet, and gas flow extraction net. And this is the mesh, right, we have for the CFD and the DM model. Right, and we also build a refinement regime around here in order to capture, in order to better capture the information coming from the powder scale, right? Because the powder scale it happens at a micro scale, right? So we did a little bit refinement here in order to resolve the boundary condition better. So let me show you the results. So let me do that. Let me replay the video. So the video you see here is showing you the flow field inside of the machine chamber. Again, this is at meter scale. So this is the net. Okay, this is the net of the gas flow. And what you see here is a jet, right? This jet is coming from the powder scale simulation. Okay, and how the particles, right, migrates in the inside of the machine chamber. So let me use this video to show you. So now you are looking from the top over the printing platform. So those red solid lines are the printing directions, and those blue dots are the dynamic shows you the dynamic process of the distribution of the powder spatters. And we did some experiment, and then we applied our computer vision techniques to extract what is the spatter distribution in the experiment, and then we do a comparison of the final distribution. I wouldn't say it is very accurate because now we have a powder bed. We truly don't know what is the initial powder bed distribution in the experiments, right? We just use the same laser power, scanning speed, and the gas flow parameters. But overall, quantitatively, right, you see similar pattern. So we feel maybe it's good enough, right? We decided to do some parametric study. So we choose 3 important parameters of the gas flow, which we feel are the most important for the parametric study. So one is the flow direction. We consider 3 directions: horizontal, vertical, and 45 degree. The second parameter is the flow rate. Here the flow rate is the maximum flow rate, the percentage of the maximum flow rates the machine allows you to use. So 20%, 35%, and 40%. And we consider use different gas types. The first one is argon, the second one is nitrogen. So this is the parametric matrix. Now let me directly show you the computational result. The final spatter distribution. So 45, this direction is the angle of the flow angle. This direction is the flow rate, and the left panel is for the nitrogen. The right panel is for argon. There are many things you can discuss. For example, right? It seems better gas flow give you better result. This is very common sense, right? Because basically the gas flow is to clear the spatter, right? Of course, better flow rate will give you better result. Another interesting tendency we found is that no matter which flow angle and the flow rate you use, it seems argon will always give you better result, right? If you compare the spatters, right? Just the better distribution, right, is always better, right, than the cases using nitrogen. So although, right, this model can give you many details, right, you will know the exact distribution of the spatters, but we still want to do some very basic theoretical analysis to rationalize this finding. So this is very fundamental fluid mechanics, right? So our basic assumption is that for given flow rate and a given particle, the higher aerodynamic drag give you better clearance performance. Okay, so if you open any fluid mechanics book, you know how to estimate the aerodynamic drag over a particle, right? Which can be computed as 1/2 times drag coefficient times the density of the gas times the velocity square and the frontal area of the particle, right? So you know that in fluid mechanics, right, drag coefficient is not just a constant, even for a simple sphere. So if you are in the no flow range or the Stokes flow range, we know that the drag coefficient is inversely proportional to the Reynolds number. And if you plug this formula back into the aerodynamic formula, you would see that the aerodynamic drag is proportional to the viscosity of the gas for the same particle and the same flow rate, right? And if you check the periodic table, you know that the viscosity of argon is bigger than the nitrogen. That's why, right, in this flow range, right, I mean, argon performs better overall, right, overall. And then if you at the high flow rate, because you don't know, right, I mean, what's the flow rate inside of the meshing chamber. So if you are in the high flow range or the Newton's range for sphere, right, the drag coefficient is a constant, typically 0.4. So if you plug in this into the aerodynamic formula, you see that the aerodynamic drag is proportional to the density for the same particle and the same flow rate. Again, if you check the periodic table, you know that the density of argon is also bigger than the density of nitrogen. So that's why no matter which flow range you are, argon always does a better job, right? Okay, so this is some applications, right, of the computational model where I just presented to you. It seems everything looks fine, but I do admit that there are some issues. I mean, this is just the issue for myself. I think it is the issue for everybody in the multiphysics modeling for metal additive manufacture, or in general, interface multiphysics problem. The issue is as follows. Remember, right, there are several boundary conditions, Neumann boundary conditions, you need to satisfy on the gas-metal interface. Because people couldn't have an explicit representation of the interface, right? So you couldn't just enforce them as a traction or flux boundary condition. So what people do is instead apply them as an interface condition, you convert the interface boundary condition into a body force through a delta function. This delta can be computed by using level set. Because you have a level set field, so you can define the Heaviside function, a regularized Heaviside function. So the delta function is the partial Heaviside function over partial level set function. So all the kinematics, flux, traction, compatibilities are satisfied in a smeared way. Because if you want to evaluate this body force, you need to have a smeared interface, right? A diffusive interface. You may feel this is fine, but let me use a simple case to illustrate that this actually can be problematic, because additive manufacturing is considered to be a high precision process, right? So we need to have some accuracy requirement. So what you see here is a heat transfer between two concentric spheres. So for this problem, for the two spheres, we have different conductivities, and on the material interface, you have to satisfy both the temperature compatibility and the flux compatibility. Now, since this is a quasi 1D problem, so we are able to derive the exact solution, which looks like this. If you use this approach or the diffusive interface approach, this is the result you get. You see your result. I don't know whether you can see that. You see the result is over diffusive, right? You see the big difference between the exact solution and the diffusive interface. Although I already used 40 elements to resolve the particle inside. And you know that 40 elements is considered to be very fine for metal additive manufacturing process, right? Because the powder is very small, right? So 40 elements can introduce a lot of computational cost in real-world application. So we feel we need to do something, right? I mean, to address this issue. So what we do here is we develop a coupled level set and the enriched immersed boundary method. So remember that in that mixed formulation, right? In the beginning, our gas-metal interface is represented by a level set. And then after that, we did an element-level triangulation of the gas-metal interface, right? So this is the triangulation of the gas-metal interface. Now, since this Bragg-Biel surface continual force doesn't give you good result, how about we do immersed boundary method to enforce the boundary condition? We immerse this triangulation, the gas-metal interface, no matter whether it has topology changes or not, right? It's a triangulation. Immerse into the background mesh to enforce the boundary condition, right? You can do that. However, I don't want to mesh the interior of the triangulation, because if you do that, I have a meshing problem, right? And then you have a different topology. This can be very tricky. So I want to resolve everything in the background mesh. However, if you have studied finite element, if you use linear finite element, you know that for linear elements, you have a constant gradient inside of the element, right? If this is your interface, and even you just consider a heat transfer, if the properties, right, across interface have some discontinuity, this Neumann boundary condition is never going to be satisfied. So you need to do something, right, in order to achieve, you resolve everything in the background mesh. So what we do here is this. After you get the triangulation, you immerse into the background mesh, you will identify what are the elements cut with your triangulation, right? For those cut cells, what we will do is for each node of those cut cells, the DOF will be the number of DOF will be enriched by 1. So every node of the cut cell will have 2 DOF. If we are talking about heat equation, 1 DOF for the temperature for the solid phase, for the metal phase, 1 DOF for the gas phase. And because now you have a more DOF, right, and then it will give you more space, right, to adjust your solution to satisfy this kink profile, right, of the temperature field in the element interior. So you can combine this concept with augmented Lagrange multiplier, and then you can derive many discontinuous Galerkin formulation for this type of problem where you need to satisfy Neumann boundary condition with the property discontinuity. So for example, this is a discontinuous Galerkin formulation we developed for conjugate heat transfer, right? So in addition to the Galerkin formulation, you will involve, several boundary integrals, right? Those boundary integrals, right, involves enriched DOF in the formulation. I will skip the math here, so if you are interested, you can check our paper in CMME last year. So I want to show you the performance, right? This is very important. So let's revisit that heat transfer into concentric spheres. So again, this is the exact solution. Now this is a solution through the EIBM approach I show you. Can you see the difference? You barely see the difference, right? And then let's show me some comparison between different approaches. As I said, right, you are able to derive the exact solution, which is the red solid line. And then this is the diffusive interface solution, which has a lot of errors, right? You see there. And you see that the accuracy of the EIBM pretty much is the same as the boundary fitting mesh. Right, boundary fitting mesh, we can handle this problem very well, but you have a meshing problem, right, which is impossible. So, and also this method converged very well as you refine the mesh. So this is the convergence study we performed for this, heat transfer into concentric spheres, right? And then this approach can be extended to other boundary condition too. So for example, you can apply this approach to handle the 7 boundary condition in solidification. Right, so this is a one-dimensional solidification benchmark problem I got from the textbook from that Dantic and the Roper. Actually, one of them is my colleague at U of I. Right, this is a one-dimensional problem, right? So normally, right, including myself, previously, if you use diffusive interface approach, you have to introduce the liquid fraction to handle the boundary condition. And I remember when I was at Northwestern University, when I worked with the diffusive interface approach, I read a lot of papers from Professor Bohner regarding the models for those liquid fraction. But this is a diffusive interface approach. And you actually, if you have the enriched immersed boundary method, you can actually enforce them in a better way by using this enriched DOF concept. So here, let me show you the result. So this result is the comparison between different approaches. We have an analytical solution from this textbook, and then what you see here is the temperature distribution at one time step, right? You see how well the enriched immersed boundary method captures the temperature gradient change, right, across the solid and liquid interface, right? Even though we are using a non-fitted mesh, and this figure shows you the time history of the solid liquid interface position, right? Very good agreement with the analytical solution, and it shows significant improvement over diffusive interface approach. Of course, right, there are many boundary conditions in additive manufacturing you need to handle, so we haven't fully extended this approach to additive manufacturing application. But what we do achieve is we have integrate this approach with a fluid field. So we are able to simulate convective conjugate heat transfer by using this enriched immersed boundary method. So what you see here is a flow past the hot sphere at Reynolds number equals 3700. So here we immerse the sphere, right, inside of the flow, right? The flow and the sphere have different conductivity ratios. Okay, so here the this sphere is still by, matched with a triangulation. It's not, reconstructed from the level set. So this is the computational domain, right? This is the background mesh, and here's the result. So it's still a fluid mechanics problem, right? So we want to first check the accuracy of how this method, capture the flow statistics. So this is the vorticity behind the sphere, and then we compare several statistics, flow statistics. So one is the mean velocity along the center line behind the sphere. Another one is the RMS of the flow of the velocity along the center line, and then the third one is the pressure coefficient on the sphere. You can all of them agree very well with the directed numerical simulation using boundary fitting mesh, right? Even though our mesh is coarser, and then we're using the immersed approach. Now the most important thing is for the temperature field, right? So this figure shows you the temperature distribution in the wake, and this figure shows you the temperature inside of the sphere. So it's a cooling process. Most importantly, right, the most important thing is for this figure. So you see that this enriched immersed boundary method can reduce, right, the relative error of the temperature compatibility and the flux compatibility to a very low, error, right? So we are able to, control the error for temperature compatibility under 5%. For the flux compatibility, it's a little bit more challenging, but we are able to control them under 10%. Even though, the property ratio, the conductivity ratio between the sphere and the flow is 10,000. So as I said, right, we haven't, applied this approach to metal additive manufacturing, but we are able to apply it to some other manufacturing process. So what you see here is a gas quenching, right? Quenching is a heat treatment process for mechanical parts. So here you have a cold gas to cool down a rotating mechanical gear, right? So what do you see here for the video on the left? Oh, sorry. Oops. On the left is the temperature evolution in the wake, and this is just some flow visualization of the vorticity, right, induced by the rotation of the gear. And then for the temperature field, here's the result. So this video shows you the cooling process of the gear, and those two images shows you, the relative error of the temperature compatibility and the flux compatibility during the simulation. All of them are reduced to, a very low level. So, we feel that, this approach can be applied to many interface-coupled multiphysics as long as there is a boundary condition. Neumann boundary condition involves large property ratio, which the interface couldn't be exactly captured, and then you still want to have a high accuracy to enforce the boundary condition. This method can be applied. So we are looking, we are working on extending this method to additive manufacturing. I hope in the future I can show some applications. So with this, let me summarize my presentation. So as I said, as an interface-coupled multiphysics problem, additive manufacturing is very hard to simulate, and to overcome the challenge, we developed a mixed interface capturing and interface tracking thermal multiphase flow formulation. This formulation leads to a mixed sharp interface and the diffusive interface approach right now. And our goal is to have a mesh flexibility and facilitate laser material interaction, right? So we will have an explicit treatment of a laser material interaction, but we don't do any mesh generation, mesh motion, or remeshing, right? And it also leads to a simple and effective pure geometry-based redistancing for level set method, and it shows some improvement over traditional PDE-based redistancing. And it's very easy to use, right? It's a geometry, right? You don't have to solve PDE. And I have shown you how to use those models, right, to predict melting point dynamics, thermal history, defect formation, propagation, and scattering. And of course, this model can be applied to other metal AM processes as well, such as directed energy deposition. So thank you very much for your attention, and I'm very happy to answer any questions you may have.
If you have a question, let me know. I'll bring the mic to you. Are there any questions?
Yes.
Oh, so it's a very nice presentation. So I have a question. You're dealing with sharp interfaces, but is there any cases where you actually might have a physically diffuse interface, where the interface is actually really is a diffuse interface, as say if you have an alloy, for example, in the solidification problem? Is your method immediately adaptable to such a case? Or is it needed for such a case?
I think we need, but right now we haven't done that. I think probably for the evaporation, right there, I mean, this is such a case, right? But right now we have only handled two boundary conditions. One is the flux compatibility, another one is the Stefan boundary conditions. But I do agree with you for some others boundary conditions you need to do that. But we haven't done yet.
Thank you. Very nice. I have a question regarding the simulation with the lasers.
Okay.
And more of a curiosity. Like a lot of lasers now in fluid mechanics and I assume also in manufacturing are pulsating.
Okay.
And so I wonder if the rate of pulsation could be adjusted to avoid the melting pot, even if the laser is stationary.
You mean the position, the orientation of the laser?
No, it's like you got, I don't know, 100 hertz or kilohertz
I see.
Laser pulsing at, I don't know, 200 millijoule per pulse or whatever it is. But if the laser is not steady, so you don't have a continuous heat flux, but you have a pulsating heat flux.
Okay.
Considering that the time scale can be adjusted, right?
Right.
I wonder if that provides a solution to avoid the
defects.
bubbling,
Right. I think this is interesting. I don't know the exact answer. Yeah, I think, but what I can tell you is in the community, people do try different strategy, right, to change the laser parameters in order to suppress the defect formation. I think the approach you mentioned definitely is a way to explore. Yeah, here I do modeling. I think computationally we can try that. We can do some simulation to see whether numerically we can do that. But I don't know the yes or no, absolutely yes or no answer.
All right,
Yeah.
Thank you.
Very nice presentation. And I apologize, maybe I didn't understand this correctly, but when you were talking about the speed of the scanning, it seemed like you talked about the force fluctuation, stabilizing. And my question was, is the faster that you go, might there be like less fusion? Or it seemed like it was asymptoting to something, but you could go so fast.
Right, that's true.
So what does that mean relative to your result? Or is that the force fluctuation is low and you just can't, it would be another graph that you'd have to look at to tell the quality of the material that's deposited or that fusion of the material? Does that make sense?
Yeah, this is a good point. If the laser travels very fast, right, you have less time to melt the material there, right? So you may end up with shallower depths, right? I totally agree with you. Yes. So our simulation is for given, for different scanning speed and scanning direction, you need to rerun the simulation. But the scanning speed and the scanning speed and the laser power has been experimentally investigated by Argonne National Lab. There are some findings there. So, for example, what they found is, like I mentioned, right, faster scanning speed leads to smaller depth fluctuation, right? That's true. And also, the scanning speed also affects the pores formation. So there is a threshold of combination between laser power and the scanning speed. It's a boundary, right? At one side you will have pores, and another side you don't have pores. Yeah.
Thank you.
Thanks.
Thanks for the great presentation. So, in your presentation, I see there you use the level set function to represent the interface.
Right.
So I see there's a bubble when do the later melting. There might be the bubble inside of the solid. So it seems like a complex level set function is required. So I'm wondering, how do you do the initialization for the level set function?
Oh, I see. I think, yeah. you know, your initialization, I mean, if there's no powders, right? It's just a straight line of the zero level set, and then you compute the sign distance, right?
Yeah.
You will have an initialization of the level set. And then if you have the powders, you know the position of each powder, right? You know the radius. So you can define, based on those information, you can define the initial zero level set. They may not be simple connected, right? But based on that, you can still compute the distance. And regarding, right, the formation of the bubbles, this is the beauty of level set method. I mean, if there is a bubble, the level set convection should capture it. Yeah. I mean, you don't need to worry that in the beginning you don't have a bubble, but later on you have a bubble. This can be automatically captured by level set. That's why we want to still have a level set in the formulation, right? Yeah, otherwise, you have to, you know, remesh.
Yeah, thanks.
Yeah.
Maybe one last question.
Hey, thank you so much for the talk. I just had a question regarding how the laser, so you showed that diagram of the melting pool, how it forms kind of with the solid powder on the outside, and then the melting pool, and then the laser kind of diffracting off of the side of the
Okay.
the
You mean
powder.
the laser reflection, right?
Yeah.
Yeah, I can
so
go to that
I'm just
slide.
curious how you model how the laser diffracts inside the liquid, and if you took that into account, because it looked like it was just you had like only one interface with the powder, like the side of the powder, and then the laser going into it. But wouldn't it refract into the liquid too? And I was just wondering if that would change the like how the liquid metal affects this refraction.
I see. No, we handle the multiple reflection, right? If this is the initial ray, right, it hits here, some energy will be resolved, right? And then this energy will be reflected. And this ray will hit here again, some energy will be resolved, and then some energy will be reflected. We keep tracking. We keep tracking that.
With the liquid metal?
Yeah, liquid metal, yes.
Okay.
We keep doing that until I think there's because sometimes, right, the melting pool can be very deep, and then once a ray hitting inside, they just go bouncing back and forth, again and again, again and again. There is no end, right? But you see that after one intersection, the reflected energy will be reduced, right? As you go on, right, the energy will become weaker and weaker, weaker and weaker, and in the end, if the energy is very weak, you don't have to consider anymore, right? But we do track all the reflections. Right. I mean, this is the gas-liquid interface. This gas-liquid interface.
Well, in the interest of time, we'll stop there. And I want to thank you very much for your talk. So everyone join me in thanking our speaker.
Thank you.